Last time we identified the four infinities that plague the Fourier transform. These theoretical hurdles make it impossible to use it on everyday random signals that we encounter in the real world. If you missed that video or any in this series on fixing your FFT, you can find the whole playlist by clicking on the info card up there in the corner. To make the Fourier transform usable in the real world, we're forced to take some shortcuts, meaning that any practical analysis is at best only an approximation of the true frequency content of your signal. This is where we have to be careful what sort of signal we present the FFT with. If we aren't mindful of how the algorithm handles these mathematical infinities and prepare our signal accordingly, we'll fall straight into the trap of garbage in, garbage out. We've already found out how to deal with the first infinity, the limits of the integral. The sort of signal we want to analyse is not going to go on forever. It will start at some finite point in time and end at some other finite point in time. For the rest of time, it'll be zero. Therefore, the result of the integral will only increase for the time for which the signal is non-zero. So long as we set the lower limit of the integral to before the signal starts and the upper limit of the integral to after the signal ends, the result of the integral will be the same as integrating over the whole of time. But what about the second infinity, integrating the product of a continuous signal, if we don't know that signal's equation? From the invention of the phonograph by Thomas Edison in 1877 to the records and cassette tapes of the late 1970s and early 80s, audio recordings were stored in analogue form, their amplitude represented by some continuous change in a property of the medium. Then, in the mid-1980s, digital recordings began to supersede the analogue ones. CDs took over, and music was no longer stored continuously, but as a discrete list of numbers. The idea wasn't new. Pulse-coded modulation, which converted analogue signals into a series of digital pulses, was developed in the 1940s, and built on earlier research like that of Swedish-American engineer Harry Nyquist, who had proposed Nyquist's sampling theorem as early as 1928. The problem was that the computing power required to perform the necessary calculations was not yet available. However, by the mid-1980s, integrated circuits were almost 30 years old, and the transistors they contained kept shrinking, making computers more powerful. This increased power meant that a discrete version of the Fourier transform could now be applied to digital audio data. To find the area under the graph of a random signal looking like this when it's multiplied by a cosine wave is not easy. However, if we approximate it using sampled versions of the signal and the cosine wave, it looks like this. The step nature of the signal means we can easily measure the area under the graph using a Riemann sum, no integration required. The same is true for the sine component. This is why the integration sign of the Fourier transform has been replaced by a summation sign in the discrete Fourier transform. So, by approximating the continuous time signal using a sampled version of the signal, we've solved our integration problem. However, here we have to be careful. The accuracy of your spectral analysis partly depends on how well you sampled your signal. Remember Nyquist's sampling theorem, which states that a continuous time signal can only be perfectly reconstructed from its samples if the sampling rate is at least twice the highest frequency component present in the signal. Even if you're dealing with an audio signal, just because you can't hear any frequencies higher than 20 kHz doesn't mean they're not there. Just ask your dog. Simply setting your sampling rate to 40 kHz is not enough. You always need to make sure that you filter the signal before sampling it, so no higher frequencies get into your signal and cause aliasing. But remember, filters have a roll-off. If you set the cutoff of your filter to 20 kHz, a portion of the higher frequency components can still squeeze through the filter's transition band. Therefore, CD audio is sampled at 44.1 kHz so that it can cope with any frequencies in the transition band and ensure they don't get aliased during the sampling process. Also, ensure that you are sampling with enough resolution. At least 16 bits are recommended for audio signals to keep quantization errors to a minimum. How about the third and fourth infinities, having to test a continuous range of frequencies over an infinite bandwidth? We actually dealt with the infinite bandwidth when we sampled our signal. We had to filter out any frequencies we weren't interested in because our sampled signal could not contain any frequencies higher than half the sampling rate. But how do we test a continuous range of frequencies? We can't, so we're going to have to limit the period of the signal. When we dealt with the first infinity, the limits of the integration, we said that so long as the signal started at some finite point in time and fell silent again at some finite point later, we could limit the period to the time for which the signal was non-zero, as the result of the integral would only increase during this time. However, how much silence we include either side of the signal affects which frequencies the discrete Fourier transform tests. Notice that in removing all the infinities we can't cope with from the Fourier transform, we've ended up with something that's beginning to look a bit like the Fourier series again. By limiting the period of the signal, we are changing it back into a repeating signal. Therefore, the frequencies the discrete Fourier transform is going to find for us are going to depend on the period we choose. Provided we ensure that the entire non-zero portion of our signal fits within the measurement period, adding more silence to either side of the signal will effectively increase its apparent period. The jump between adjacent frequencies in the Fourier series is equal to 1 over the period, so a larger period will allow the discrete Fourier transform to find more intermediate frequencies, increasing the frequency resolution and closer approximating the true frequency spectrum of the non-repeating signal. Unfortunately, this is not always possible, and even a really efficient implementation of the discrete Fourier transform, like the fast Fourier transform, can have trouble processing very long signals. The fast Fourier transform algorithm, proposed by James Cooley and John Tukey in 1965, revolutionized digital signal processing by reducing the computational complexity of the discrete Fourier transform. Their key innovation was to apply a recursive divide and conquer method originally proposed by Carl Friedrich Gauss in 1805 to break down the DFT calculation into smaller, more manageable pairs. This divide and conquer approach dramatically reduced the number of calculations needed to compute the DFT, making it practical for a wide range of applications in signal processing and communications, as well as many other fields. The only caveat was that the signal had to contain a number of samples that was a power of 2. Now, in theory, you can take a signal of any length, pad it with zeros until a power of 2 length is reached, and run the FFT on it, thereby analysing the whole signal at once and getting a pretty good frequency resolution to boot. The only problem is that as efficient as the FFT is, the speed at which you can run it is still limited by the length of your signal and the amount of processing power you have available. This is where FFT size and windowing comes in. Remember those 2 parameters I was playing with in Audacity's spectrum analyzer at the beginning of the talk? But what role do these settings play in preparing our signal for the way the FFT handles those theoretical infinities? How can we ensure we're giving the algorithm the best possible chance to find the real frequencies hidden in our data? We've spent the last 2 videos gradually stripping away the 4 infinities of the Fourier transform just to make it run on a computer. But here's the hard truth. The FFT is a rigid mathematical machine. The result it gives you is only ever going to be as good as the data you give it to work with. This is what could be wrong with your FFT. If you aren't mindful of the assumptions it makes to cope with those infinities, the algorithm won't actually analyse your signal at all. It'll end up analysing the mathematical artifacts created by those very assumptions. To show you exactly how to fix this, I've prepared a series of deep dive videos which you can receive by email. These lessons will show you why and how to prepare your signal to get the most accurate results. Simply click on the link right here. Fill in your email address and receive the lessons direct to your inbox. There, you'll learn how to ensure that your next FFT analysis stays as accurate and as artifact-free as possible. I'll see you there.